Hi, in this talk, I will present our work on cache-friendly IP reassembly network function. This is a joint work with my other colleagues at Nokia Bell Labs, Fang Hao, TV Lakshman, Sarit Mukherjee, and Limin Wang. Before presenting our work, let me briefly touch upon the problem context that has motivated our work. Large enterprises with geographically distributed branches typically have requirements to interconnect their branch locations and public-private cloud infrastructures over the internet for various business needs. And the required enterprise networking is typically defined based on strict policies that involve connectivity, QoS, and security. To address these complex requirements of wide area enterprise networking, the concept of the SD-WAN was proposed. In the SD-WAN architecture, there is a centralized SD-WAN controller whose responsibility is to set up and maintain networking policies required by the enterprises. And the SD-WAN gateways are provisioned on enterprise premises and individual branch locations, and they are programmed by the controller to perform various network functions, including traffic steering, slicing, encryption, decryption, filtering, etc., according to the enterprise interconnection policies. In this environment, SD-WAN traffic is typically heavily encapsulated with tunnels in order to support various application-specific, tenant-specific network slices and to secure connectivity between branch offices and cloud networks over the internet. It is expected that by 2022, SD-WAN traffic will become as much as 30% of all WAN traffic. In this emerging and increasingly popular SD-WAN architecture, SD-WAN gateways play a central role since they perform necessary data plane processing. But the fact is, the typical SD-WAN gateways available on the market are realized with general purpose hardware for flexibility, and these hardware boxes usually come with a limited number of CPU cores, and therefore the efficiency of these software network functions is very critical for successful SD-WAN deployments. In particular, IP reassembly is one of essential network functions in SD-WAN environments because the heavy encapsulation of network traffic increases the chance of IP fragmentation. While there are mechanisms to prevent IP fragmentation, none of them is actually sufficient, and IP fragmentation is something that cannot be avoided in the wild. So the question we are asking in this paper is whether the existing design of IP reassembly network function is optimal and efficient enough. Before answering this question, let's take one step back and consider the typical network functions execution model. In the kernel bypass paradigm, which is quite established in the NFV workload nowadays, the most dominant NF execution model is per packet run to completion. Although this model is designed to achieve high performance packet processing in user space, a question is whether the model is still desirable for a complex network function such as IP reassembly. Our observation is that this run-to-completion model may not be an ideal design choice for relatively complex network functions because of increasing pressure on instruction cache. To illustrate the impact of instruction cache pressure, we performed the following experiment. Here we consider a hypothetical network function called a scrambler. What this function does is to simply rewrite the source IP address of every incoming packet in 4 distinct steps, as shown here. Each of the 4 steps reads the source IP address from the packet, apply a complex hash function to it, and write back the source IP address field with the computed hash value. In the right-hand side, we re-implement this function by applying simple loop transformation to the original implementation. So essentially, we split the single for loop into 4 different loops, and now each of the 4 rewrite steps occur in its own loop. This loop transformation is called loop fission, and it is in fact a well-known code optimization technique, which is supposed to reduce instruction cache misses and register pressure. The implication of this simple loop transformation on network function performance is shown here. The split loop implementation shows 18% higher packet processing throughput than the single loop counterpart. And the reason for improvement is because of the 16% lower stall cycle in the CPU front end. The lower stall front-end cycle means there's less delay in instruction fetching and decoding due to less instruction cache misses. This result makes perfect sense because split loops have much leaner body loops, which can be cached more easily than the larger single loop body. This result suggests that for a complex network function, per stage batch processing may in fact be more desirable than per packet run to completion because of instruction cache performance. Now let's see how we can apply this lesson to IP reassembly network function. So the problem here is that unlike the hypothetical scrambler function that we just saw, many real-world network functions, including IP reassembly, are not designed with clear-cut multi-stage processing in mind. Let's see how the state-of-the-art IP reassembly is designed. As you can see here, based on classic per packet run to completion model, it first retrieves packet from Rx, and for each packet, it checks for fragmentation, and if the packet is fragmented, it reassembles it into a full IP packet, and look up destination port for the packet, and finally transmit the packet through TX. Although the main loop body consists of multiple steps, in fact, pretty much the entire processing overhead of this function is dominated by a single reassembly API, which triggers complex nested function calls with side effect. Such design is not instruction cache friendly because for each packet, multiple different functions need to be reshuffled in the instruction cache. So essentially, we need to revamp this monolithic API design and re-architect overall functional logic as multi-stage. We end up developing 7 processing stages for IP reassembly function as shown here. In order to benefit from cached instructions, the initial Rx step retrieve a large batch of packets, typically 128 or 256. The rest of the steps then perform more granular processing, whose complexity is reasonably low. Another benefit of this granular processing is that, unlike the original design, where reassembly processing and the frag table cleanup logic are intertwined, we completely decouple them into separate steps. One issue with this multi-staging design, however, is that there are 2 branches coming out of frag check step, as you can see. One branch is followed by fragmented packets, and the other branches is followed by non-fragmented packets. These 2 branches are then later merged back before the TX stage. Such data flow can in fact introduce out-of-order packet delivery when a mix of fragmented and non-fragmented packets are received. We solve this problem by reassembling fragmented packet in place within the original packet array without rearranging packet positions in the array. So far, we focus on instruction cache performance. As for data cache, the most memory-intensive operation in IP reassembly is frag table lookup. Frag table is essentially a hash table that temporarily holds all received IP fragments for reassembly. So for every received IP fragment, we need to look up the frag table to get a corresponding frag entry. During frag lookup, a frag entry, which contains both frag key and frag data, is loaded into data cache, but we only need to access frag key, not the frag data. Since the size of frag key is 1/4 of cache line in this design, we are essentially wasting 75% of cache line doing linear probing. We address this problem by partitioning the frag table into 2 regions, one for frag keys and the other for frag data. And we allocate frag key array in a contiguous memory region so that we only need to load frag keys into data cache during frag key lookup. And also we can load multiple frag keys into a single cache line at once. We implement the proposed design by refactoring the DPDK's official IP reassembly implementation and evaluate its performance. The left-hand side figure shows that our design can support line rate processing for up to 20% fragmented traffic, whereas the original design can only sustain 5% fragmented traffic. In the right-hand side, we look at where the performance improvement of our design comes from. As I presented earlier, Our design incorporates several features, and here we add each of these features to the prototype one by one and look at how much each feature contributes to the throughput performance. As it turns out, the most dominant performance boost, about 20%, comes from multi-stage processing, and the other two features each contributes about 5 to 7% additional boost. In this talk, I presented our work on cache-friendly IP reassembly network function. While this work specifically focused on a particular network function, a broader takeaway from our work is that when designing a network function, instead of blindly adopting a run-to-completion model, one has to pay attention to the implication of instruction cache pressure, especially if the network function involves non-trivial complexity. Beyond the IP reassembly network function, we are currently planning to investigate and profile the cache performance of other types of real-world network functions, and based on this investigation, work toward a more generalized tool that can guide code optimization for network functions. Thank you.